Okay, so good morning. Can you hear me well enough? Okay, good, thank you. Yes, well, it's really an honor to participate in this commemoration of Professor Benders because he has not only had enormous influence on the field of optimization, but also on me, since I've spent several years doing research that's closely related to his original idea. So, as you probably know, Benders decomposition is one of the best known and most successful optimization methods. In fact, in my opinion, it is the most successful optimization methods for solving large-scale problems, particularly due to the fact that it's been generalized in various ways in recent years. And one of its virtues is that it obtains optimal solutions. It's not a heuristic method. And of course, the secret is to decompose the problem into a master problem that contains some variables that, when fixed, causes the problem to simplify radically. And that simplified problem comprises a subproblem. And in many cases, this subproblem itself decouples into smaller problems, which really accelerates the solution. The key to making all this work is to have communication back and forth between these two problems so as to achieve optimality, and that's done through Benders cuts, which of course is the key idea in Benders decomposition. So this is a graph that came from a survey article on Benders decomposition. It was published back in 2017. And as you can see, the number of mentions of Benders decomposition in the literature began to explode exponentially about the year 2000. And today, the explosion continues. There are countless papers now that use Benders decomposition, as well as many applications. So why this explosion? Well, in the early years, in courses, we were told that Benders decomposition is a clever idea, but it tends to converge slowly. Well, people began to discover about 20 years ago that's not true. If you implement the method correctly, it can be quite efficient. And we also have generalizations now of Benders, including logic-based Benders. Now, there is a limitation in classical Benders decomposition, and that is that the subproblem I mentioned must be a linear programming problem, or in Jeffrey On's generalization, a continuous nonlinear programming problem, because you need the dual variables or the Lagrange multipliers to obtain the Benders cuts. So how do we overcome that? There are many cases where a problem does decompose very nicely, but the subproblem is not a linear programming problem. Nonetheless, there is a spark of genius in the problem-solving strategy of Benders decomposition. This is what, in fact, attracted me to this field. The idea is so clever, so original, it seems to come from nowhere. In fact, it's an interesting question to me. Where do these new ideas come from? Now, this was a radically new idea at the time, and in my view, it's a powerful idea, and we're just now beginning to appreciate its full potential. So by exploiting the underlying problem-solving idea, we can actually generalize Benders and address many new applications. So what is the idea? Well, as I mentioned, the dual solution of the subproblem is expressed in terms of dual multipliers, which gives you a Benders cut. What's really going on here is that this dual solution is a proof of optimality for the subproblem. So you have a proof that your solution of the subproblem is optimal. Well, the idea is to use that same proof schema, but with different premises. Excuse me. That is, you begin with the same proof, but you change the values of the master problem variables, which adds different premises to the same proof of optimality, and you use that same proof to construct another Benders cut that helps you determine which of solutions to avoid in the future as you iterate the method. So what we're going to do is to exploit this idea in logic-based Benders. That is, we're going to use the fact that the dual of the linear programming subproblem is a proof. It's actually a subset of logic. We have a logic-based interpretation of what's happening here. And we're going to use that proof as a mechanism to construct generalized Benders cuts And this allows the subproblem to be any problem you want, at least in principle, as opposed to a linear programming problem. And of course, this opens the door to many more applications. So this is how we get logic-based benders. In many cases, you see speed-ups of several orders of magnitude. And in my experience, even in the early days, we were obtaining speed-ups on the order of 10,000 or more relative to state-of-the-art. And state-of-the-art is quite good in optimization, such as in mixed integer programming. Now, one potential drawback is that you have to handcraft Benders cuts for every problem class. You can't just pull them off the shelf in most cases. Well, this is an inconvenience, but it's also an advantage because there's something called the free lunch theorem. And that theorem says that you can't really solve a problem effectively without exploiting that problem's special structure. There's no free lunch. You have to work. In fact, this is why they pay my salary, right? Because every problem requires a different approach, and this is my job to find that. So this generalized form of Benders allows you to exploit the special structure of problems, which is usually necessary in combinatorial optimization. So this is how the classical Benders work. So I'm going to show you the classical method, and then we're going to generalize that to logic-based. So we have a problem here. The x's are going to be the complicating variables. When you fix these variables, the problem becomes easy, and these are the remaining variables, and we have constraints. And as you see, when you fix the x's, this becomes a constant, and so you have just linear constraints left. So this is these x variables, the complicating variables, appear in the master problem. So what you do is you find a starting value for the x here, then you pass that value to the subproblem, which is the problem that remains after you fix the x. And this problem usually decouples and becomes much simpler. You solve this problem and you obtain a proof. This is a linear programming problem now. This dual solution U is a proof of optimality, and you use this to obtain a Benders cut that looks like this. And you send this Benders cut back to the master problem, and this constraint gives you some guidance as to which value of x you should look at next. So you solve the master problem subject to the Benders cuts so far generated, and that tends to allow you to focus on the solution values of x that are closer to the optimum. In effect, what you're doing is to compute the projection of the problem onto the x space a little at a time. Okay, so that's the classical Benders method. Now, how are we going to generalize that? Well, we do it like this. So now we have a more general problem. You see, the constraint set can be anything you want, okay? And the master problem now, again, you're looking for a value of the x, the complicating variables. Fix that, and you get a subproblem, which probably is going to simplify a great deal by decoupling, perhaps. Then you solve this by obtaining a proof of optimality. That proof we're going to view as the dual solution, right? So we're generalizing the idea of dual so that a proof is a solution of the dual. And that proof is going to give you a Benders cut in a way I'll show you shortly. And we put that back into the master and do the same type of iteration as in the classical method. So you see, we're exploiting this core idea of using the proof of optimality as a mechanism to obtain Benders cuts. Okay, so in my view, this was a brilliant idea. Okay, it has enormous potential. Okay, so what's this stuff about duality? So this is the general optimization problem you might want to pose. And this is the dual that we use. The dual is the problem of deducing the tightest possible bound on the objective function from the constraint set. You can see that as a generalized dual. Okay? I call it an inference dual. In fact, all the duals we use in optimization are special cases of this. For example, linear programming dual. This is a linear programming problem. The inference dual is the same thing. It looks like this, just specialized. You're deducing the tightest possible bound on the objective that can be inferred from the constraint set. Now we're going to apply something that people learn in Optimization 101 called the Farkash lemma, which says that we have implication here if and only if there is a vector of multipliers, non-negative multipliers, that allow you to take a linear combination of the constraints and deduce a bound on the optimum. Okay? That's just elementary theory. So we take that problem, rewrite a little bit like this. This is equivalent. Now we can get rid of this z variable. And then you get the linear programming dual that appears in the textbook. So actually, thousands of students have studied linear programming duality, but no one seems to know where it comes from. It's just falls from the sky. Actually, this is where it comes from. It's an inference dual. Now, there are several duals we use in optimization: Lagrangian duals, surrogate duals, subadditive duals, and so forth. They're all special cases of inference duality using a different inference method to obtain the dual. So in the classical dual, we use non-negative linear combination as an inference method. If you use Schwarzschild-Gomery cuts and integer programming, you get the subadditive dual. If you use branch and bound, you get a branching dual. This is actually the branching tree you use to solve integer programming problems is a dual solution. You can view it as a dual. Okay. Now there's a variation of Benders that I call branch and check. Okay. And it goes like this. When you solve the master problem, very often you solve it by branching, such as in integer programming. And as you solve it at nodes of the search tree in the branching method, you obtain feasible solutions now and then. When you obtain a feasible solution, you can send that to the subproblem and generate a Benders cut, but you put back into the master problem. And that way we only need to solve the master problem once, but we strengthen that problem as we go along by adding Benders cuts on the fly. This turns out to be a better method in many cases because you only have to solve the master problem once. I should say, by the way, this is not branch and cut. People often say, well, this is just another case of branch and cut, which people use in integer programming. No, it's not. It's very different from branch and cut. And here are some of the reasons it's different. And the main reason it's different is that the type of reasoning you use to obtain these cuts is totally different than the reasoning you use to obtain cutting planes in classical integer programming. Okay, so this is how this sort of came about. This is the history, of course. This is Benders' original paper up here, okay, and it was generalized a decade later by Geoffrey Ahn for nonlinear subproblems. Then along came a person who was very influential on me, Robert Jarislow's, who was actually trained in formal logic. And he pointed out that there is a connection between linear programming duality and propositional logic, namely a unit resolution proof, which I won't explain today, but that type of proof in logic can be interpreted as obtaining a dual solution to the linear programming problem. So there is just a connection between linear programming and logic. I should say, by the way, that the connections between logic and optimization go very deep, very extensive, and wonderful connections between the two. And I spent a lot of my career trying to understand those. Okay. The first clear application in retrospect is a paper that I did with a student of mine, a former student, to verify logic circuits. Okay, and a general statement of logic base came around in 2000. The first really extensive computational work was done by a colleague of mine, Ignacio Grossman, a year later. Branch and check was computationally tested in that same year by a former student of mine. And there's another paper I did with Greg Odeson in 2003. And Corrado and Fischetti also applied this idea to the special case of mixed integer programming. They called the Benders cuts combinatorial Benders cuts. There's a lot of literature on that. It's a special case of branch and check. So that's brief history of what's been going on. Okay, so let me give you an example to make this more concrete. This is one of the original examples, original application. So we're going to assign tasks to the machines, and we have to schedule those tasks on each machine subject to time windows. Okay, well, the scheduling part decouples by machine. There's a separate scheduling problem on each machine, and that's going to be the subproblem. The scheduling part is going to be the subproblem, and the assignment of jobs to a machine will be the master problem. Very natural decomposition. The objective here is to minimize the make span. So Benders, by the way, has the advantage that you can solve the master problem and the subproblem by different methods. Pick the method that works best. So in this case, the master problem is going to be solved by mixed integer programming, which is very good at assignment, but mixed integer programming is very bad at scheduling because the relaxations are weak. On the other hand, constraint programming is probably the state of art for scheduling, so we'll apply that to the subproblem. So again, we exploit this advantage. You can solve the two by different methods. So here, we have the assignment task in the master, we have the scheduling in the subproblem, then we use constraint programming to obtain a proof of optimality, and we generate a Benders cut. The Benders cut, the simplest possible Benders cut looks like this. And it says, if you assign the same jobs to the same machines again, you're going to get the same result. Okay? So don't do it again. That's what this Benders cut basically says. It's called a no-good cut. It's a very, very simple cut. Okay? So this won't get you very far. But what you want to do is to identify a subset of the jobs you assign to machines that actually are responsible for that solution. Some of the assignments don't really make a difference. They don't affect the objective value of the make span. So you identify the jobs that really contribute to the solution, and those are going to become the jobs that you avoid assigning to those machines in the future because you know the solution will be the same. Okay, so how do you identify these jobs? Well, the simplest way is just to trial and error. You remove some of the jobs from the assignment, resolve the subproblem a few times, and see what happens. See if you get the same result. And this sounds like a stupid way of doing it, but in most applications, this works wonders. This little trick alone will get you a speed up of 10,000 over state of the art. Okay, using these simple, strengthened, no-good cuts. There are various methods for strengthening these cuts. Most of them deliver irreducible cuts. That is, you can't make them any stronger. Greedy method, deletion filters, and so forth and so on. I like quick explain. It came out of the constraint programming literature. Okay. Now, if you want to become smarter, in fact, most applications become really better treated with analytical cuts that exploit the problem structure of the problem you're trying to solve. And this is where we really get into the meat of Benders decomposition. So just to give you an example, this is what an analytical Benders cut looks like for the machine assignment and scheduling problem. It looks something like this. I won't go into the details, but the point is you can exploit what your understanding of the subproblem and use that to generate more intelligent logic-based cuts, okay? Because you understand the structure of the proof mechanism that underlies it. As a result, we get a catalog of different types of logic-based cuts. I mentioned the no-good cuts, the strengthened no-good cuts, the analytical cuts, also explanation-based cuts. These are cuts that are based on the actual proof that the subproblem solver uses to obtain optimality. You look at that proof and you derive from it Benders cuts directly from the proof. Now, most solvers don't tell you how they actually solve it. They don't give you a trace of the solution process, but recently, we're seeing solvers that do so, particularly in satisfiability and constraint programming, and you can use that information. In fact, we now have 2 general-purpose logic-based Benders solvers that do exactly that. And I'll give you an example of that later. Okay, so this is some computational results. These are very early results, but this is the number of instances we solved in a given amount of time. Notice the logarithmic scale. So this is the Benders in the blue line up there, okay? And this is state-of-the-art MIP, okay? This is a solver. It's been perfected over about 50-year period, right? Engineered to death. So even for problems that solve this many problems, we're talking about a factor of 10,000 difference in the time. Okay. Another nice application is to stochastic optimization. And in these models, typically you have a large number of possible scenarios, each of which has a probability. And you want to try to, say, maximize some expected cost, or expected revenue, or minimize expected cost. So the problem here is that the problem is huge because you must introduce variables for every possible outcome that could occur with a certain probability. Well, this is just perfect for Benders because you can put these scenarios into the subproblem, and the subproblem decouples by scenario, okay? And then becomes much better. Well, this has been done before in the standard method, so-called L-shaped method, okay? And they use something called integer cuts in this method. Well, the integer cuts are actually simple, no-good cuts. So what you have to do here is don't use simple integer, no-good cuts. Use smarter logic-based cuts. If we view this as a case of logic-based Benders, we can exploit that fact. And this can give you enormous speed up. So here's an example. This is a comparison of stochastic scheduling with a large number of scenarios, up to 500. Okay, so very soon, the state-of-the-art integer L-shaped method becomes intractable. Okay, but branch and check, which I mentioned earlier, just sort of knocks this off. No problem. This is actually quite recent work with a former student. Another example I like, in fact, I work with a company on this, is home healthcare scheduling. More often today, healthcare is given at a person's home because it's safer, there's less communication of disease, it's cheaper, and so forth. And here, an important problem is to schedule and assign healthcare givers to the patients, because these healthcare workers must travel from home to home to work with the patients. So I worked with a company and applied logic-based Benders to this problem. This is what the master problem looks like. I won't explain the details, but just to show you how it might look. And as you can see, it's a mixed integer programming problem with 0, 1 variables. Okay. This is the subproblem, which is a constraint programming problem. It has typical constraints from constraint programming. And this becomes a separate problem that's solved for each of the healthcare workers. So we schedule each worker separately. And since a worker can only visit no more than 4 or 5 patients per day, these small decoupled problems can be solved very quickly. So we exploit that fact and they get enormous speed up in the solution of these home healthcare problems, which are quite difficult. They're very difficult problems. We use strength and no good cuts here, similar to what I described earlier, and a branch and check method. Okay. And here's some computational results. So mixed integer programming is the green. Let's see. Yeah, this is branch and check down here. Yeah, this is the computation time versus the number of new patients we're accepting during each period. Okay. And again, we have a logarithmic scale. So computation time for mixed integer programming, well, it blows up fairly quickly. This is logic-based Benders, and the green is branch and check. So here's a case where branch and check is the superior method by about a factor of 100 over standard logic-based Benders, although as you get up to large problems, it loses its relative advantage. But here again, we're able to solve problems significantly larger than before. Okay, and this is a real data set from a team in Denmark that schedules home health care. And as you can see, well, MIP basically times out, very soon. And the branch and check is working very well for these instances. All right, now satisfiability, the satisfiability problem has been addressed by an entire community now for some years. There's a huge literature on this. And the satisfiability solvers are extremely good. It's something like the mixed integer programming solvers. They're very well engineered. They're extremely fast. They can solve problems with millions of variables. The key to these SAT solvers are the so-good conflict clauses. So basically what you do, you have something like a branching search, which is like in branch and check. And at various nodes of this branching search, you check for feasibility. And if it's an infeasible subproblem at this point, you generate a cut, a constraint that captures the reason for this infeasibility. And the way that we check for feasibility is to apply unit resolution. Remember I mentioned that earlier in that problem with circuit verification? So they apply unit resolution to check for feasibility, and they identify the variables that are responsible for the infeasibility and use that to generate a so-called conflict clause, which is precisely a strengthened Benders cut. It's a strengthened no good cut that we use in Benders. And here, the subproblem method is a logical inference method. Okay, and the solution to that dual problem is a proof of infeasibility. Okay, in fact, this type of conflict clause actually appeared in the Benders literature 1 year before it appeared in the satisfiability literature. We discovered it first. All right. Okay. Now I thought I might take you through a few applications. just to show you the breadth of applications that Benders can now accommodate. These are all logic-based Benders. I don't normally plug my books, but I'll do it in this case because this book, which came out last year, contains a description of 147 applications that were published in more than 200 articles, and in each case explaining how the Benders method is applied and the cuts generated. Okay. All right, so let's just look at a few examples. These are transportation examples. As you see, bicycle sharing is one of my favorites. Okay, container ship, as you may know, container ship industry is the core of our world supply chain, and the literature on container shipping is enormous now. This is one of the major applications of optimization. Here's an example, managing a container port. I'm sure you know about this here in the Netherlands. I spend part of the year in Los Angeles, and I have within sight of my apartment is the port of Long Beach. Okay, one of the largest container ports in the world, and we see something like this. This isn't done haphazardly. Everything that happens in this port is very carefully timed and managed to optimize the usage of cranes and so forth. Okay, this has turned out to be a major application of logic-based Benders. There's a number of papers in this area. And of course, production, task assignment and scheduling was the original example I showed you before, a very early case. There are also job shop and flow shop applications because there's a natural decomposition there. Assembly line balancing was also a very early application of Benders, one of that proved the usefulness of logic-based Benders. Peugeot applied this very early on in their assembly line plants. And the object there was is to decide which plants would assemble which model of the car, and then to sequence those cars on the assembly line. So there's a natural decomposition, an assignment, and a sequencing problem. So Benders was very useful there. Today, of course, we have work cells in Japanese style, and Benders has been used for that purpose. Also, maintenance issues have been addressed by logic-based Benders. Other elements of the supply chain, again, we see probably the largest fraction of Benders applications is in production and supply chain issues, okay, which keeps our world moving. Your Amazon package, right, is delivered with the help of Benders decomposition. The way that shelf space is allocated in a warehouse is done very carefully. The way the robots move around, to pick the shelves, that's can be governed by Benders. When they pack the merchandise into the boxes, which items do they put in a single box? That can be solved by optimization problems. It has been using Benders. The delivery problem, and of course now some companies are using drones in combination with the trucks to deliver packages. That can be solved with Benders. And so it goes, okay? One of my favorite examples is the first one here. This is probably the largest problem that I know that has been solved by logic-based Benders. This was solved in the US. A few years ago, there was a massive auction to allocate portions of the electromagnetic spectrum to users, such as cell phone users, mobile phone users, radio, television, and so forth. So to determine the outcome of the auction, it was necessary to solve an enormous optimization problem with tens of thousands of constraints. And most of these constraints were non-interference constraints. It is to say that if you have two mobile antennas for your phone that are too close together, you must make sure the frequencies don't interfere. Okay, so these non-interference constraints add up to tens of thousands of constraints. These constraints were put into the Benders subproblem. Okay? And that Benders subproblem is not a linear programming problem, it's a combinatorial problem. But by using logic-based Benders cuts, it was possible to solve this problem. It was a problem that was just barely solvable, but Benders made it possible. So if you're in the US, using your phone, you can thank Professor Benders that your phone works. Okay. What else? So there's a number of other network applications and telecom. When you use your phone here in Europe, I'm sure, Some of the processing is done by so-called edge computing. It's allocated to processing units in the internet. How are tasks assigned to those units? That's been done by Benders. Okay. And on it goes. So you see in the logic circuit verification at the bottom, the very first application of logic-based Benders. Okay. The medical element. Well, here again, there's a number of papers on operating room scheduling. That's a huge problem for hospitals because the duration of surgery is so unpredictable. There's a lot of stochastic models here. Ideal application for Benders because it decomposes, okay, into assignment of surgeries to operating rooms and then the scheduling of those surgeries within each room. And of course, you schedule the staff, the doctors, and so forth as well. Kidney exchange, such more abstract problems like DNA sequence alignment has been addressed by logic-based Benders. And the Chinese have been very much on top of dealing with COVID, as you probably know. They have very thorough regulations for dealing with that. So we have a number of papers in the literature on how to manage COVID vaccine, also test center locations. And Benders has been applied to these problems as well. Unfortunately, there's a number of disasters. The number seems to be increasing with climate change. So we now have a subfield in optimization that deals with disaster management. Now, these applications are mainly with respect to earthquakes, which have been around a long time. But you also see applications with dealing with floods and other weather-related events. So you see all of these applications have been dealt with using Benders. Most of them are stochastic in nature. A very important one is restoring electric power. You have limited number of crews. You know, how do you allocate those crews? Another is search and rescue, right? So the people are trapped in these ruins, and you know, how long do you spend trying to rescue people from one site before going to the next? An excruciating problem that has been addressed with optimization models to do the best we can here. And Benders has been used for that. Wildfires. I don't think you have these in the Netherlands, but in the north, of course, in Canada, Siberia, and so forth, also in the U.S., it has proved very difficult to fight these wildfires. We can't seem to control them. But that problem has been addressed with Benders decomposition. How do you position your crews so as to stop the spread of the wildfire? And here's some other applications. It goes on and on and on. A colleague of mine, Mike Trick, works in the area of scheduling sports. Schedule the teams, the games, the referees, and so forth. Another is an ideal application of Benders because this problem decomposes. Scheduling courses. I don't know how they do it here in Technical University, but some schools are now using constraint programming as well as Benders to schedule your courses. Okay. I should say, by the way, that we hear so much about AI and how AI is changing the world. Well, yes, AI is in the media, but the world actually runs on optimization. Okay, almost everything we do is, you know, you switch on the light switch. How does that work? Well, the coal that's mined is governed by optimization algorithms. The commitment of the units, the generating units, the unit commitment problem is a classical problem in optimization. The design and scheduling of the electric grid is controlled by optimization, and on and on and on, right? So practically everything we do is regulated by optimization. Without it, our world would be impossible. Okay, AI is interesting, but optimization still runs things. Okay. Also, some abstract problem classes. So I mentioned the first one, the satisfiability problem, is essentially, not only essentially Benders, it is an instance of logic-based Benders, precisely. Okay, one of the earliest. 0-1 programming can be done with Benders, optimal control, linear. So this one, operator counts and automated planning. Very often those robots in Amazon warehouse are regulated by an automated planning A-star search. Okay, a crucial element in in designing these algorithms is something called operator counts. Okay? Well, it turns out that estimating operator counts is an ideal application of logic-based Benders. And a paper pointing this out won Best Paper Prize recently at an ICAPS meeting, a meeting on automated planning. And on it goes. Okay, so I mentioned earlier that there are two off-the-shelf software packages that apply actually branch and check. Okay, what they do is to apply constraint programming or a satisfiability algorithm to the subproblem, and the conflict clauses they obtain are used as Benders cuts, as logic-based Benders cuts. So the subproblem, constraint programming solvers now often generate these conflict clauses as part of the solution process, and you can access those as a user. So these are the two software packages I know of. MiniZinc is a constraint programming, modeling, and solution package developed in Australia. Nutmeg is actually developed by some of the same people, okay? And it's more specific for branch and check. So should one use an off-the-shelf solver for Benders? Well, I think it's sort of in between. These solvers don't exploit the special structure of the problem, okay, which is one of the strengths of logic-based Benders. On the other hand, they're often better than off-the-shelf mixed integer programming or other types of traditional solvers. So I think you get some of the advantages of Benders by using off-the-shelf. You might try one of these first. If it doesn't work, then you have to go deeper and earn your money, no free lunch, and earn your money by exploiting the structure of the problem. Okay, so this is my conclusion. The inherent potential of Benders decomposition, this brilliant idea, is still unfolding before our eyes 60 years after its invention. It's remarkable. So thank you.